Okay, you are able to see the screen?
Yes, sir.
Okay. Okay then. Okay, so we have seen open circuit test, and open circuit test is done to determine the core losses, and you have to apply rated voltage, and it is independent of the current. Okay, you have to apply rated voltage. So that's what we have seen how to perform the open circuit test on a transformer. Next we will see the other test, which is called as short circuit test. So as I have already stated, this test is used to determine the ohmic or copper losses in the transformer. Okay, so by using this test, we are going to find out copper losses in the transformer. Right. So can you say whether I should apply rated voltage or rated current when you are performing this test? Can anyone say?
Rated current, sir.
Rated current. Okay, so in the open circuit test, we have seen the core losses depends upon rated voltage, so you have to apply rated voltage when you are performing open circuit test. But when you are performing short circuit test, our objective is to find out the copper losses at full capacity. Okay, or the copper losses when the transformer is fully rated. Okay. So that means your objective is to find out the copper losses at rated current. Okay, so copper losses at rated current is given by a general formula, which is IFL whole square into equivalent resistance of both the windings. Okay, so IFL whole square into equivalent resistance of both the windings. Let's say RE1. We have already seen what is RE1. RE1 is equivalent resistance referred to primary side. 1 indicates primary. Okay, so RE1 is nothing but R1 plus R2 dash. Okay, so that means equivalent resistance referred to one particular side. Okay, that multiplied with the rated current square in that winding, that will give you the copper losses. Okay, that is nothing but I square R losses. So when I say full load copper losses or rated copper losses, that current I should be I full load. So I full load whole square into equivalent resistance. That will give you the total copper losses of both the windings. We'll see that. The low voltage.
Sir,
Yeah.
sir, can you explain why, sir, current is used to rated current is used to short circuit test performance?
Okay. So your question is why the rated current should flow in when you are performing short circuit test. Is that your question?
Yes, sir. Yes,
Okay.
sir.
Right. Okay, so copper loss basic formula I have given, right? So what is that? Simply it is nothing but I square into R. Okay.
Yes, sir.
Right. So if I is not rated, okay. So what is, first of all, we'll see what is rated means. Okay. Let's say I have 20 kVA transformer. Transformer rating we have told already in terms of kVA. And next what they will give, V1 by V2 or E1 by E2 they will give. Okay. Right. So let's say I give you 20 kVA transformer and 100 by 1000 volts. Okay, let's consider 100 by 1000 volts is your primary and secondary side voltage ratings. Okay, what is the rated current on the primary side? Can you say? 20 kVA is your
0.1.
transformer rating, 100 volts is the primary voltage, LV voltage value. So what is the rated current on the LV side?
0.2, sir.
20 kVA, 20 kVA
kVA.
divided by 100.
Yes,
Okay,
sir.
so 0.2 kVA maybe. Okay, that means 200 amperes. Okay,
200 amps.
200 amperes. That is called as rated current on the primary side. What is the rated current on the secondary side for the same transformer if your secondary voltage is 1000 volts?
1000. Sir, it is 10.
20 kVA divided by 1000. So it should be 20 amperes.
Voltage. Yes, sir.
Yeah.
20.
So that means kVA divided by the voltage on that particular side. If it's LV, it is low voltage, it is HV, okay, whatever it may be. So kVA divided by voltage of that particular winding, okay, on that particular side. That will give you rated current. That is called as rated current. Okay. If you are not, so that means when the rated current is flowing, what is the formula? I rated whole square into resistance of that winding, okay, whatever it may be. Okay, right. If you are not flowing the rated current in the transformer winding, and if you are, let's say you are sending only half of the rated current, can we say that copper losses as full load copper losses? No, because the full load copper losses is defined or is calculated which corresponds to the rated current in your winding. Okay, so if you are not sending the rated current, and let's say you are sending only 50% of the rated current, then you have to say that these copper losses are not the full load copper losses. These copper losses are corresponds to 50% of the copper losses. Okay, right. You can send less than the rated current also, but you have to specifically say that the losses when I am sending this much current are not full load copper losses. They are this much percentage of the full load copper losses. Okay, right. So but you have to generally give me the rated copper losses only. Okay, when you are calculating the efficiency, the transformer supplier will give you the efficiency at full load. I will say 98% is the efficiency at full load. He has to say that. Okay, right. So he has to calculate the efficiency under full load condition. So you have to calculate core losses at full load and copper losses at full load to find out the efficiency at full load. Okay, got it. So that is the reason why we are trying to find out the full load copper losses by performing this short circuit test. To find out full load copper losses, you have to send the rated current in that particular winding. Okay, then only we'll call it as full load copper losses. Okay, so that's why we are sending rated current. Right, and if you see, copper losses depends upon current. They doesn't depend upon the voltage. Okay, right. So if I am sending the rated current in the transformer winding, that is good enough to find out the copper losses in the transformer winding. It is not depending on the voltage. Clear? So that's why, since it depends upon the current, you have to make sure that you are sending current in the primary winding and secondary winding, and you should make sure that if you are sending the rated current, then only we'll call it as rated copper losses. So that is the reason why we are trying to send rated current. Is it clear?
Yes, sir.
Okay. So the LV side of the transformer is short circuited. That's the low voltage side, and the instruments, that is voltmeter, ammeter and wattmeter, are placed on the high voltage side. So that means you are placing the instruments on the HV side, and low voltage winding is short circuited. Okay, right. The primary applied voltage is adjusted by the auto transformer to circulate rated current in the HV side. Okay, so that means we are actually calculating what is the rated current, that is kVA divided by HV, high voltage, whatever it may be, and you are arriving at some value of current, and you are trying to send that much current through your ammeter. That means your ammeter should indicate that calculated value of current. Okay, so in the present case, HV, in the example what you have considered, HV is 1000 volts I have told. So 20 kVA divided by 1000 volts. So that's a 20 amperes. So 20 amperes should be indicated in your ammeter. Then only rated current is flowing in the primary winding as well as in the secondary winding. Okay, right. So to circulate the rated current in the HV side, since I1 N1 is equals to I2 N2 approximately. Okay, so I2 that is on the LV side is also the rated LV current. Okay. If you see, we have already stated I1 by I2 is equals to N2 by N1. Okay. Right. So if rated current is made to flow on the primary side, that means HV side in this case, automatically rated current will flow on the secondary side also, that is LV side. Okay. Only the small error is excitation current, that is very small, so that we are going to neglect here also. Okay. So approximately I1 N1 is equals to I2 N2. So when your ammeter is showing rated current on the primary side I1, automatically rated current will flow in the secondary side also. Okay. If you want to cross check, you can connect an ammeter and check, not an issue. Okay. Approximately rated current will flow in both the windings. Okay. So how to perform this test? Our objective is to make sure that your current is the rated current flowing in your ammeter. That's all. Okay. So a primary applied voltage of 2 to 12% of the rated voltage is sufficient to circulate rated current in both HV and LV windings. What does this statement mean? A primary applied voltage of 2 to 12% of the rated voltage is sufficient to circulate rated current in both HV and LV windings. What is the meaning of this statement?
Sir, as you told in previous, 230 voltage applied to low primary side.
Yeah.
But in this case, only 2 to 12% of 230 volt is applied to perform this test.
Yes. What you have stated is exactly correct. So that means there is no worry for us to see whether I have applied rated voltage or not. It is immaterial. Okay, whatever voltage I'm applying. My objective is to make sure rated current flows in the primary winding. That's all. Okay. If you make sure your rated current is flowing, then if you see the voltmeter reading, you will observe that it will be between 2 to 12% of the rated voltage only. Okay, let's say your primary side, let's say 100 volts I have told. Okay, so 2% will be maybe 2 volts and 12% maybe 12 volts. Okay, so it will be in this range only. Okay, right. So only 2 to 12% of the rated voltage is seen in your voltmeter, but your rated current is flowing in the both primary and secondary windings. Okay, right. So from the equivalent circuit, if you see, out of this 2 to 12%, I mean half of that, around 1 to 6% of the rated voltage is applied across the core or the shunt branch. Hence, the core losses are very small compared to copper losses at rated voltage. You are understanding now? Since 2 to 12% is sufficient of the rated voltage is sufficient to circulate rated current, only 1 to 6%, that means half of this 2 to 12% is applied across your shunt branch in your equivalent circuit. Shunt branch corresponds to the core of an actual transformer. Okay, so you are not applying rated voltage across the core. You are applying only 1 to 6% of the rated voltage. So that means the core losses which are occurring in this scenario are not the rated core losses, because you have applied only 6%, maximum 6% of the rated voltage. Okay, so core losses still exist, which are very small. Okay, right. So which are very small compared to rated core losses. Okay, so in this scenario, we can assume that these core losses are very small and can be neglected. Okay, and the wattmeter reading, whatever is shown, is straight away equal to the copper losses of both the windings. Is it clear? Right. Since 2 to 12% is sufficient enough, so that means the voltage what you have applied across the transformer is very less. Since the voltage is less and the core losses are proportional to the voltage, since the voltage what you have applied is very less, so the core losses which are occurring in the transformer core in the present scenario are very less and they can be neglected. And if you neglect that, the losses which are indicated in your wattmeter are nothing but the copper losses of both the windings. Is it clear? So the wattmeter reading is considered as the rated copper losses or ohmic losses of both windings. Core losses are small and are neglected. Okay, right. At primary applied voltage of 2 to 12% of the rated voltage, the excitation current in the shunt branch is also small and can be neglected. That means this is the equivalent circuit. For the present scenario, short circuit test, this is the equivalent circuit. That means excitation current is very small, so we are going to neglect that. Neglect means it's open circuit, so excitation current is 0, we are assuming. So ISC, which is seen in your ammeter, is nothing but your short circuit current. VSC, which is seen in your voltmeter, is nothing but the short circuit test voltage. Okay, and wattmeter straight away will give you the core losses. Is it clear?
Yes, sir.
No, sir. Sir, didn't get, sir.
So what is the doubt?
Sir, it is the left hand
In this
left
circuit?
hand or in the circuit, sir, circuit.
Yeah.
Sir, this circuit is at the left hand or the right hand?
No.
In primary or secondary?
No, this is the equivalent circuit referred to primary. Right. So here, if you see here, this is your HV.
Then, sir,
Okay, wait. This is your HV and this is your LV. So LV will have R1, RLV and RL and XL. Correct now? Primary side. That means HV side will also have R1 and X1. R1 here is RHV. X1 here is XHV. Okay, if you talk in terms of HV and LV. So that means R1, L1 will be there here. R2, L2 will be there here. Rx2, okay, whatever it may be. Okay, so if this resistance is transferred onto primary side, and if the secondary reactance is also transferred on the primary side, and your excitation current is very small, and if you are neglecting, in that scenario, this is your circuit. Got it?
okay, sir. Then, sir, why this dotted
What?
dotted thing in circuit?
Dot here.
Yes.
It's open circuit, na? It's open circuit. Shunt branch is there, but it's open circuit. That's all.
Okay.
Got it. So that means excitation current is equals to 0. If excitation current is there, it should flow through this branch, but excitation current is very small and we are going to neglect it. So that's why IE is equals to 0. That means it's open circuit. Open circuit means no current is flowing. Okay. That's all. Right.
Sir,
So then, yeah.
so why primary side is high voltage?
Okay. So this is a very valid point and very good question. Okay. So I have stated that. Okay. So in the present case, rated current should flow in the primary and rated current will automatically flow in the secondary. That's what this statement says. I1 N1 is equals to I2 N2. Correct now? If rated current I set on one winding, automatically rated current will flow on the secondary winding. Correct. Okay. So for let's say 20 kVA 100 volts by 1000 volts transformer. So this will be 1000, right? HV is 1000. LV is 100. Okay. So if rated current, what is the rated current value on the primary side, on the HV side? Rated current, how you will calculate? 20 kVA divided by 1000 volts, how much?
So
20
20.
kVA, 20 amperes. So 20 amperes is the rated current. That means if I choose an ammeter which has the capability of carrying 20 amperes, RMS current is sufficient enough for me to deal with. Clear? Right.
Yes, sir.
And what should be the rating of your voltmeter?
So it will be 2 or 12% of 230.
Okay. So maximum 12 to 15%. Okay. 15% of 1000 volts is something like 150 volts. Correct?
Yes, sir.
So that means 20 amperes is available with me, and 150 volts voltmeter is sufficient enough to perform this test. Let's consider your question. That means why it is HV. So let's shift all these parameters onto the LV side. Okay. So what is
Okay,
the rated current now on the LV side?
So
What is
what was the voltage, sir?
voltage LV? I have already stated now 100 volts. So 20 kVA divided by 100 volts. How much?
Sir, 200.
200 amperes. So that means I should have an ammeter which is of higher rating. Okay. So 200 amperes. Okay. And right. So getting that kind of ammeter is very hard for me. And dealing with 200 amperes is more dangerous for the person who is operating rather than dealing with 20 amperes. Okay. So that is
Yes,
the
sir.
only reason why that means the instruments are of lower rating. So those are very easily available in your market. And you are dealing with lower current rating. So that is also good for you. Okay. Right. So that is the reason why we are conducting short circuit test with instruments on the HV side and open circuit test with instruments on the LV side.
Okay.
Okay. Same thing applies for open circuit test also. Let's say open circuit test, your objective is to apply rated voltage. If you connect all the instruments on the LV side as shown here, LV is 100 volts, so you can use a voltmeter which is of 100 volts. But if you are connecting instruments on the HV side, you have to use a voltmeter which is of 1000 volts. Okay. Right. So getting instruments and working with that voltage level is safe for the person operating that. So that is the reason why OC test is done with instruments on LV and HV side open circuit. And short circuit test is done with instruments on HV side and LV short circuit. Is it clear?
Yes, sir.
Okay. So whatever way you do, whether you connect on LV side or HV side, your losses are going to remain same. Okay. Core losses, if you perform test by connecting on LV side or HV side, your losses will be same. Short circuit test, if you perform by connecting instruments on HV side or LV side, your losses will be same. Losses are not going to be affected. Okay, so that is only for your safety and availability of instruments we are connecting in this fashion. Okay, so the excitation current IE is assumed to be 0, and this is your equivalent circuit. So now you know VSC, voltmeter reading, ISC, ammeter reading, PSC, which is your wattmeter reading in the present scenario. So ISC is the rated current in the primary, that means HV, high voltage winding. Okay, so what will be the impedance? That is V by I. So V you already know from the instrument, I also you know from the instrument. So ZEH, because this will give you the total equivalent impedance. Okay, so ZEH, complete circuit impedance, both primary and secondary. So ZEH is VSCB divided by ISC. REH, how to calculate? You know the wattmeter reading given by PSC, that wattmeter reading divided by ISC square. That means your ammeter reading square. So that will give you resistance. Once you know ZEH and REH, you can calculate XEH. EH means refer to high voltage. Okay. So X is given by, sorry, here it should be minus, I think so. Right. Right. I think here it should be minus, right?
Yes, sir.
Right. So because that is root of R square plus X square, so this should be minus. Okay. So you should place minus. So you can calculate XEH also in this fashion. So you know the equivalent resistance referred to HV and equivalent reactance also referred to HV. Okay. All these impedance parameters calculated using these formulas are referred to HV side as the meters are placed on the HV side. Okay. Right. If the leakage impedance parameters of both primary and secondary are required separately, then it is usual to take as RH, which is shown in the figure, is equals to RL dash, which is shown on the figure, is equals to REH divided by 2. I hope you got it. Because this equivalent circuit what is shown on your screen is the equivalent circuit referred to HV side in the present case. Okay, so the total resistance REH using this formula divided by 2, that will be equal to the resistance on the HV side, that is equals to the resistance referred to HV side from LV side, that is RL dash. RL dash indicates the resistance which is referred to HV from LV. That's what RL dash. Okay. L indicates from where I am coming, and dash indicates I am not the actual one, I am coming from somewhere. Okay. Right. So we have already seen this. So similarly, XH is equals to XL dash is equals to XEH divided by 2. Got it? So that means
Sir,
by, yeah.
Sir, RH and RL, R dash L will be same if N2 equal to N1.
Why N2 and N1 you are linking to this? No.
Because R dash L and X dash L are coming from N2 N1 relation, sir.
Okay. So you say me the formula for RL dash is in terms of RL.
Sir, it is N2 by N1 square. Sorry, N1 by N2 square into RL.
Right. So that formula what you have stated is valid till now. Okay. So what I am trying to say here from this thing is, you are asking this only, na, regarding this only, right?
Yes, sir. Yes, sir. Yes, sir.
Okay. From the instruments readings, you have got these C formulas. That means you have calculated XEH and REH. So this REH is the total equivalent resistance referred to high voltage winding. Okay. If you remember, we have already stated this formula. RE1 is equals to R1 plus R2 dash. You remember
Yes,
in the
sir.
past. Okay. So this R2 dash is nothing but RL dash in the present case. Right. So we are assuming that those two will be approximately equal. Okay. Because they are referred to, now they are referred to one winding on the primary side. So RH is equals to RL dash is equals to REH divided by 2. Okay. It is not RL, it is RL dash. Okay.
Yes,
You
sir.
got it?
Okay, sir.
Okay.
Sir, it is assumption only.
No, actually, I mean, it will approximately equal to this value only. Okay. It is not like an assumption. Okay. Because what you have indirectly stated, that is also correct. It depends upon the turns ratio also. Okay. Y means this RL dash you are calculating, that means REH you are calculating from the voltage and current on the primary side, on the HV side. Okay. So that means I have already stated RL dash is the equivalent resistance which is seen from the source. You understood?
Yes, sir.
RL dash is the equivalent resistance which is shown from, which is seen from the source in the primary winding. But actually this RL dash fellow is related to secondary winding. Okay. But it is the equivalently what is seen from the source. Okay. Right. But if you want to find out actual value of resistance RL dash on the secondary, obviously you have to multiply with N1 by N2 whole square or N2 by N1 whole square. Okay. So it depends upon the turns ratio. What you have already told, na? So that is correct. You got it, na?
Yes.
Right. So indirectly what it means is, if you have number of turns more, obviously the wire length is going to be more, and the wire length is more, then obviously resistance will also be more. That's what. The both are interlinked. So what you told is the same. Right. Okay. So this is how you have to perform your short circuit test, and from that you can calculate the resistance and reactance of both the windings. Okay, and from open circuit test you can calculate RC and XM. Okay, so all the equivalent circuit parameters, what you have seen in the equivalent circuit, can be calculated by performing these two tests. Okay, one test will give you core losses straight away, another test will give you copper losses, rated copper losses straight away. Got it? Right. So short circuit test gives information regarding ohmic losses, nothing but copper losses at rated current and frequency. The equivalent resistance REH and the leakage reactance XEH of the transformer are also calculated. The voltage regulation can also be determined from the short circuit test. Okay, that we'll see later. Okay. Right. So the open circuit test and short circuit test are required for calculating equivalent circuit parameters and efficiency of the transformer. Okay. Right. So we have seen how to get the equivalent circuit parameters, how to calculate efficiency once this open circuit test and short circuit losses are given. That we'll see when we study the efficiency of the transformer. Okay. So is it clear to everyone or any doubt with regards to these two tests? Right. It's clear now to everyone.
Yes, sir.
Yes, sir.
Okay. Okay then. So we'll go ahead and we'll see one problem based on transformer circuits. Okay. Right. So it's a simple thing only, this problem. So let's see. So a 33 kVA. So transformer rating is in kVA and 2200 by 220 volts. That means HV voltage by LV voltage they are giving. And 50 Hz single phase transformer has the following parameters. Okay. Primary winding, that means HV. Primary here. HV side resistance R1 is given as 2.4 ohms. Reactance is given as 6 ohms. Secondary winding, LV side resistance R2 is given as 0.03 ohms and X2 is given as 0.07 ohms. Right. Now the question is, find the primary resistance and leakage reactance referred to secondary. Okay, that is your first part. Find the secondary resistance and leakage reactance referred to primary. Okay, so let's see first one. Find out the primary resistance and leakage reactance referred to secondary. That is the question. So try to calculate that. Secondary is LV. Okay, so they are asking what is the equivalent of R1 in the LV side. Try to do that.
Three, sir.
You are trying to calculate, right?
3.
Question is, find the primary resistance and leakage reactance referred to secondary. So that means in the secondary side, what is the equivalent resistance? That means one R1, if I transfer
3 and
to,
7, sir.
that means they are asking R1 dash. Okay,
3 and 7.
3 and 7. How you have done?
Sir, we had that one, sir. R2 dash equals to R1 into N1 by N2 whole square.
Okay, so what you have done in that?
Same X, sir. We get to 3 if we do like that.
But what is the question in the here? You are talking about answer B or answer A for this? The first part, that means A, find the primary resistance and leakage reactance referred to secondary.
I'm telling
That
B,
means
sir. B.
you are telling B. Okay, so the first part is they are asking refer to secondary. That means in the secondary, what is the equivalent of primary and primary resistance and leakage reactance? That means you have to calculate R1 dash. R1 refers to primary. R1 dash is referred to secondary. Okay, so R1 dash you have to calculate, and X1 dash also you have to calculate. So what will be R1 dash and X1 dash?
Sir, R1 dash should be 0.024.
0.024. How you have got it?
Sir, R1 into N2 by N1 whole square.
Okay, so R1 into N2 by N1, so 2.4 into 220 divided by 2200 whole square. Okay, so you will get approximately 0.024. Okay, what about reactance?
0.06.
Right, so R1 dash, that means, please remember the terminology. Primary resistance refer to secondary. When I say dash, this one indicates primary. Okay, in the present case primary is HV. Okay, dash indicates I am not the actual value, I am coming from somewhere else. Okay, so primary resistance refer to secondary. Okay, if it's directly primary resistance, I will call it as R1, that's all. It is referred to secondary, that's why I'm calling it as R1 dash. Okay, so R1 dash is equals to R1 into N2 divided by N1 whole square, so which is 0.024. So in the present case, primary voltage is 2200 and secondary is 220 volts. Okay, primary reactance refer to secondary, so same formula here, it will be reactance. So X1 into N2 divided by N1 whole square, so which is 0.06 ohms. Right, so this is only a normal formula which we have already seen. So if you apply that, you should be able to get these two answers. Right, so hope everyone understood this, right?
Yes, sir.
Okay, then find out part B. Find the secondary resistance and leakage reactance refer to primary side.
Sir, 3 ohms and 7 ohms.
Okay, so R2 dash we will call it as now. R2 dash is equals to R2 into N1 divided by N2 whole square. Okay, so 0.03 into 2200 divided by 220. So it will become 3 ohms and 7 ohms. Okay, I hope everyone is able to do this, right? Only normal formula is only there, that's all. Okay, right. C, what is that? C, find the equivalent resistance and leakage reactance refer to primary and secondary. That means the total equivalent resistance. That means RE1 and XE1 they are asking. Next RE2 and XE2 they are asking. So try to calculate RE1 and XE1. You understood my question? What will be RE1 in terms of R1 and R2? You say that formula?
Sir, R1 plus R2 dash.
R1 dash.
Okay, so RE1 is equals to R1 plus R2 dash. So you know already R1 and you know already R2 dash. Simply add up those two, that will give you RE1. So what is that value? 5.4.
5.4 ohms, yes, sir.
Okay, so 5.4 because R2 dash is 3 ohms and R1 I think it is 2.4. So total will be 5.4. What about XE1? Try to calculate XE1.
7.06 ohms.
7.06. I don't think so.
No, wait. 6.
So 13.
13 ohms.
13 ohms because X1 you already know 6 ohms is given in your question itself, and plus X2 dash you have to do, and X2 dash you have calculated just now 7 ohms. So 7 plus 6 will be equal to 13 ohms. Right. So this is your first part, which is 5.4 ohms and 13 ohms. Similarly, you can find out the equivalent resistance referred to secondary side also, which is nothing but RE2. So RE2 is R2 plus R1 dash. Remember this terminology clearly, right? RE2 means equivalent resistance referred to secondary. So secondary resistance remain as it is and R1 dash will come into picture. So R2 plus R1 dash. So what is that? We have already seen R2 is 0.03 you have given and R1 dash you have calculated 0.024. So total will be 0.054 ohms. Similarly, XE2 is equals to 0.13 ohms. Try to calculate that. It's a simple thing, only that basic formula you have to know and you have to know the terminology. That's all. So if you are clear with that, you should be able to do this. Right. So hope everyone is able to do this, right?
Yes, sir.
Yes, sir.
Okay. Okay then. So next we'll see one more problem on this. Okay. So everyone is clear, right? So I'm moving to next question. Okay. So question 2 is a 20 kVA 2500 by 250 volts 50 hertz single phase transformer gave the following test results. Okay. So open circuit test they have conducted and short circuit test they have conducted. Okay. So open circuit test. We already know open circuit test. All the instruments will be placed on the LV side. If you remember, high voltage is open circuit. Okay. So the instruments are placed on the LV side. Okay. Right. So they have conducted the test. So obviously rated voltage they should apply. So rated voltage is 230 volts. So that means your voltmeter reading is 230 volts. In that scenario, the ammeter reading is 1.4 amperes and the wattmeter reading is 105 watts. That's what they have given. Okay. So the reading of voltmeter, ammeter and wattmeter for open circuit test is given. Similarly, short circuit test also they have done and the reading of voltmeter is 104 volts. Okay. As you know, rated voltage need not be applied, but rated current should flow. Okay. So rated current is 20 kVA divided by 2500. If you do, you will get approximately 8 amperes. So rated current is flowing and the corresponding voltmeter and wattmeter readings they have given. Okay. Question is compute the parameters of the approximate equivalent circuit referred to HV and LV. Right. So this is the question. Okay. So equivalent circuit parameters refer to HV and refer to LV. You have to find out and then draw the equivalent circuit. Okay. So how to proceed for that? Open circuit test will give you V0, I0 and W0. So from this, we have already seen we can calculate RC and XM. Okay. So please try to do that using the basic formulas. You remember those formulas, right? So how to calculate RC and XM? To find out RC and XM, what we should find out first?
So we have to first cos theta.
Okay. So try to find out cos theta naught.
It's a 0.3.
Okay. So after that, what do you have to find?
IC.
Okay. So try to find IC and XM also. And then try to find RC and XM from that. All of you please try to do that. Find out cos theta, then find out IC, then find out IM, and from that RC and XM.
Sir.
Yeah.
So RC is 595.23 ohms and XM is 187.19 ohm.
Okay. Right. So let's see that. But before that, we will give some time for others also to do. So others also please try, and whether we'll see whether you are also getting same answer or not. What is your IC value?
Sir, IC is 0.42.
0.40 amperes. What about IM?
So something 1 point something, sir.
Okay. Okay. So did any one of you got the same answer? Any other student?
Sir, I got IC equal to 512.
0.512. Okay. So why there is a difference between your answer and previous answer? Okay. So how you have calculated IC?
Sir, I got 0.42,
0.42. What is
IC.
cos theta naught? Cos theta naught?
0.3.
Okay. Okay. So let's check. With my answers, which is correct. Okay. Right. So first of all, you should remember that these instruments are connected on the LV side. So the RC and XM, what you are going to calculate, those are referred to LV side. Okay. Referred means you are getting those values already in the LV. Okay. Okay. So PC is given as V naught into I naught into cos of theta naught. It's a open circuit test. Okay. So PC is equals to W naught is equals to 105 watts given in the question. Cos theta naught you have to calculate from this. If you do that, you are going to get 0.3. That will be your no load power factor. Once you know theta naught you can calculate from cos theta naught. Okay. So from that, IC is equals to I naught into cos of theta naught, which is 0.42 amperes, as some of you have already told. And IM is equals to I naught into sin of theta naught, which is going to be 1.335 amperes. Okay. So I hope you all got this answer. Okay. It's easy only. You know the readings of wattmeter, voltmeter, and ammeter. Simply you have to find out cos theta naught and then find out IM and IC. Once you know IC, how to find out what is the formula for RC?
Sir, E1 by
V1 by
IC.
IC.
E1 by IC will give you RC. So in the present case, V1 is nothing but V0 is nothing but E1. Okay. So 250 divided by IC, whatever you have calculated, 0.42. Right. Maybe that will give you your RC. Okay. So 250 divided by 0.42. That will give your RC. So this is RC which you are getting on the LV side. Right. So that you should keep in mind. Okay. And XM on the LV side is equals to 250 divided by 1.335, so 187.26 ohms. Right. So did everyone got this? Or anyone has doubt in regarding this?
So got
Got it, na? So hope everyone got this. So these are the formulas what we have seen in the open circuit test. So the same formulas we are using to calculate RC and XM. Right. So next, you have calculated only these two parameters can be determined. Okay, what are parameters that can be calculated using open circuit test data we have already calculated. Now we will move to short circuit test data given to you. So what we can calculate from short circuit test? What parameters?
Sir, RH, R dash L, XH, and X dash L.
Okay, so those four can be calculated using short circuit test. Okay, so here they have given 104 volts, 8 amperes, and 320 watts. So how to calculate ZEH from this?
So voltage by current, sir.
Okay, so 104 divided by 8 should give you ZEH. Okay, and how to calculate REH?
So 320 by 64.
Okay, 320 by 8 square, 320 divided by 8 square. So that will give you 64, something like that. So try to calculate.
So
Z
RH,
E-
so
yeah,
ZE is 13, sir.
13 ohms. Okay.
Yes, sir.
And what about REH?
5 ohm.
5 ohm. Okay, others also please try to do that. So let's see whether you are getting same answer or not. Did anyone got same answer?
Yes, sir.
REH.
X is 5, and Z equal to 13, X is equal to 12.
Okay, so let's see that. Okay, so short circuit test on the HV side. So VHV is 104, ISC is 8 amperes, PSC is 320 watts. So power is equals to I square into R. If you use that formula, you can calculate resistance, equivalent resistance on the HV side. Okay, so this will give you the complete resistance referred to HV winding, REHV. Okay, remember that. This is not specific to one particular winding. It is the equivalent resistance referred to HV side. So ZEH is V by I. So you have got 13 ohms. So from that you can calculate XEH using this formula, root of 13 square minus 15 square, so 12 ohms. Okay. Right. So this is the information you can get from short circuit test. So now they are asking you to draw the equivalent circuit referred to what they asked. Refer to HV side first. Okay, so they are asking the equivalent circuit referred to HV side. So HV side is nothing but the primary in the present case because 2500 is on the primary side. Okay, so try to draw the equivalent circuit. Approximate equivalent circuit, not the exact equivalent circuit, approximate equivalent circuit. You remember now, approximate equivalent circuit means your shunt branch will be very close to the source. So what will be there in the equivalent circuit? So it could be something similar to this. Okay. Correct. Now, this is the approximate equivalent circuit referred to primary. In the present case, primary is HV winding. So equivalent circuit referred to HV will be something like this. Okay. Right. So RC and XM. Okay. So what will be RC and XM in this equivalent circuit? Right. So you have drawn the equivalent circuit similar to that or not? You are able to hear me, right?
Yes, sir.
Yes, sir.
Okay. So when you talk about equivalent circuit, this should be your approximate equivalent circuit. Okay. So they have not asked specifically what is RH and RL dash. Okay. So you can leave at this point itself. Okay. Right. So this will be the equivalent circuit, 2500 volts on the primary side, HV side, and RCHV, because RCLV you have already calculated, which is 595 point something. but they are asking the equivalent circuit referred to HV side. So that means you have to transfer that resistance RC, what you have got in the calculation, because that is referred to LV. To HV, if you want to transfer, then you have to multiply with N2 by, N1 by N2 whole square. So that will be 59523. Okay, right, 59523 ohms. Similarly, XMHV will be this much value. So those two will be present in your equivalent circuit, and REHV, because this is already referred to HV side, there is no change, so it will remain as it is. And reactance, also no change, so that will remain as it is. That's all. So this will be your approximate equivalent circuit referred to HV side. Got it?
Yes, sir.
Right, because resistance and reactance, which are already coming from the HV side data, open short circuit test, so they remain as it is. But RC and XM, what you have calculated, they are coming from LV side data, so you have to transfer them into HV side. So that way, that's why it has given this much value, 59523. Now, what will be the equivalent circuit referred to low voltage side? In that case, your REHV and RELV, REHV, XEHV will be changing. So RELV will be REHV into N2 divided by N1 whole square, so it will be 0.05, and XEHV will be 0.12. Okay, so these two remain as it is, because RC and XM already coming from the LV winding test data, so they are not going to be altered, but these are going to be changed based on the turns ratio. Got it? Right, I already told equivalent circuit means shifting the shunt branch close to the source. So here they have asked refer to LV side, so LV is 230 volts. So we have shifted that shunt branch close to the 230 volts. So this is this values, and this RELV and XELV you are going to calculate using this formula from REHV and XEHV. So that will be placed here. So this will be the equivalent circuit referred to LV side. Got it? You understood or not?
Yes, sir.
Okay. So only thing here is, if the test data is given only to specific winding, LV or HV, okay, so the parameters what you are going to calculate from the test data are confined only to that particular winding. But if your equivalent circuit is asked to refer to one particular winding, then accordingly you have to choose whether you have to multiply with factor or not. Okay. Is it clear? So this is the equivalent circuit referred to LV side. I hope everyone got it. So any doubt is there, ask me.
Sir, can you take to before slide?
Yeah.
Okay, sir.
Okay. Okay then. So hope you got it. If you have any doubt, you can ask me in the next class. Right.
Sir,
So that
595.23 is given, sir, already.
590 point. That's what on the HV side. Now you have already calculated. From the open circuit test data, you have already calculated 595.23.
Okay, sir.
So that is LV side only, na? Now equivalent circuit referred to LV only they are asking. So no change will be there. It remains as it is.
Okay, sir.
Got it? Okay then, fine. That's it for today. So we'll continue our discussion in the next class. Maybe on Thursday, maybe. Tomorrow is a holiday, right? Okay. Okay then, we will meet in the next class. Fine.
Thank you, sir.
Thank you. Yeah, thank you. Thank you all of you.